that, we can actually start applying the concept of force, the concept of the first law and second law, all right? And the third law always shows up in different applications. So that's the key. So we can apply Newton's laws in different situations. So if we have a situation of equilibrium, we talk about that last class when we did the exercise on the spring, right? So let's say I give you, so you have a roof, and then you have two cables, and they are holding a mass. That could be a question I can ask on a test or even a quiz. The only thing I will ask you for now will be to do the forces diagram on that situation there. What you will need to do, what you will need to know as well, is that the angles here, say this is 37, and this could be 45. All right. So to do a problem like that, you will need to first study what's going on that body. Normally, you will remove that body, and then you will start drawing the forces acting on it. You can start on the picture, and then we can move it to another, right? So, first of all, always the force of gravity, mass times gravity because of, right? Then you will have the tensions. So you have tension 1, tension 2. I'm sure they are different because the angles are different. If the angles were the same, then the tensions would be the same. But because the angles are different, then you put this T1, T2. Tension is a force that you normally experience when you pull something with a rope, string. So as you can see there, right? Let me see if I can do something about that. That's better. Much better there. Okay, so as you can see there in the screen, T1 and T2 are different, and you can actually already see the free forces acting on the body. Now, the key word is that they are in equilibrium. So what you will need to write here, remember that force is a vector. So you will have here that T1 plus T2 plus mg, and you can even put vector, 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 is equal to 0. That's because they are in equilibrium. When they're in equilibrium, the net force is equal to 0 newtons. So here, 0 newtons, 0 newtons. So that's a good way to start. All right? Now, of course, when we did vectors, right, I did show you how you could solve a problem like that if you were given the value of the mass, right? So just very quickly here, so you can see what I mean by that is you will bring this body here on the x and y coordinates there, and then you will put tension 1, tension 2, and mass times gravity there. What's interesting is that this angle is 45 and this is 37. How? Because of parallel lines. Alternate interiors in geometry, right? This angle is this angle there, this angle is this angle here. Okay? So that's about it. We did problems like that. Remember in the first week or second week, you will break into components. But I'm not gonna ask you for now to do that, okay? Just for you guys to know. And then you can find both tensions if you do it like that. Okay? That's a good way. So it's a very nice example to show you forces diagram, equilibrium, and how we use Newton's laws, because that one that we use there is the first law. The body will remain in equilibrium, unless the next force, unless for example I push it, right? Then the object will start to accelerate. That's the one there. Let's do another problem that is a bit more interesting. We can start doing it with equilibrium, and then we can try and do it with acceleration. I'm talking about inclined planes. So this is a situation 1. The next situation I'm going to do it there, right, will be a situation with inclined planes. And inclined planes is another common situation in physics. Right? So that's that. Inclined planes. So let's start with equilibrium in inclined planes. For an inclined plane, you will have there, you have a mass, m, and then I have an angle here, theta. There. How can it be in equilibrium if there's an angle, if it's an inclination there? Because we're going to now add friction. All right? So let's suppose here there is a mu. That mu that you see there, that is a coefficient of friction. And we're going to put here mu s. There is a question in the homework that asks you how many types of friction there are. 2, kinetic, and static. So that is static friction there. So what's making the object fall, or at least trying to fall? You will say, well, this guy, mg. But mg is pointing downwards. What about along the plane? What you will do is this very nice thing. You will draw this line perpendicular, all right? The mg is also perpendicular, and by doing simple geometry, you will find that this angle is also theta. So that is vectors upside down, all right? If this angle is theta, what you need to remember is that we can find a component that makes the object fall. This component is mg sine of theta. And then we can also find this one here. Action, reaction, right? Action, reaction. We have an action here. We have a reaction. We call that the normal force. That's the normal there. If we have that, then we know that the force of friction is the normal times mu s. So the friction is always acting opposite to the body. That's the friction there. Fs, static friction. So then you just will do mg sine theta equals to the normal times mu. But that normal there is a way to find it. Mg sine, here will be mg cosine theta. because of the way you break it into components. So I know that the normal is mg cosine theta. So you will write here mg cosine theta times mu. Look what happens, right? Mass cancels, gravity cancels, and then you get a nice result. Tangent of theta equals to mu. Right? Again, you won't be tested that on Tuesday, sorry, but I think it's a good idea to do this so it can help you to understand a little bit of the applications. I'm applying there Newton's first law and also third law, right? The action equals to the reaction. That's called the normal. And remember that the normal is perpendicular to the surface, all right? And we get friction by multiplying the normal times that coefficient, right? That coefficient is a constant depending on the surface, and it doesn't have any units. Okay, so it looks okay there, the equilibrium and the inclined planes. Let's do a problem now. Now with numbers, using a little bit of friction, but now with an object that is moving. All right, we didn't do that last class. So let's see an object that is moving under a force and when there is also friction. Okay, so you can see how we use them. And that will be an application of Newton's second law. All right, so this was the first and third law. No acceleration. The net force acting on both cases was 0. So the object was there, static, not moving. All right. So let's see. Now let's do a problem with numbers. So Newton's second law. There you are. So pretty much we're gonna have a body in a horizontal table which is 10 kilograms of mass. The body is being pulled with a force of 150 newtons. The problem is asking you find the acceleration of this body if there is friction with mu kinetic equals to 0.2. So the coefficient of kinetic friction is 0.2. So that will be a problem that you could get in a test. So let's see how will you address it. All right. If there was no friction, force divided by mass will give you the acceleration, so 15 meters per second squared. But because there is friction, it should be less. Let's see how much less. So remember, the net force is equal to mass times acceleration. What's the net force acting on this body? So we need to, well, we have a force there, we need to draw them, like we did there, we need to draw them, but this one is easier because it's in a horizontal table. So the only thing you have to do is mg. Now gravity is how much? 9.8 meters per second square. So this is mg. 10 times 9.8, 98 newtons. But we also know there is a normal by Newton's third law, action, reaction. And because there is a normal and there is mu, we know as well, we also know that the kinetic friction equals to the normal times mu. Now, what's the value of that normal? When the body is on a horizontal table, whatever the weight is, if there's no other forces pushing it towards it, because you can have a situation where, like, for example, this chair, right? The normal of the chair will be just the weight of the chair. But if I press it, the normal will be bigger. Because on top of the weight, I'm pressing it, right? But in this case, there's not that. So just the normal equals to 98. So in that equation there, 98 times 0.2, that will give you the value of the friction, the kinetic friction. So my kinetic friction will be 98 times 0.2. That will give you 19.6 newtons. Now let's find the net force. Because remember, friction acts in this direction here. That will be the friction equals to 19.6. So what's the net force? To the right, 150. To the left, 19.6. So my net force will be 150 minus 19.6 equals to what? The mass of the body times acceleration. See? That should be how much? 130.4 equals to 10.8. So then the acceleration will be 13.04 meters per second squared. So less, as you expect, with friction, there is less acceleration, right? So that problem there is actually a good example, all right? The other ones were more to visualize Newton's laws, but this one here is a nice application, all right? We can probably do another one. I'm thinking we did Hooke's law, we sort of is centripetal force, it's just application. This one I like it because it includes a friction. We did the airplane problem using kinematics, all right? And then, well, the concepts of Newton's laws. So let me just start sharing here. There. What do we have there? We have a nice diagram, flux diagram, that shows you the changes in motion caused by forces which come in pairs, right? So if they come in pairs, according to Newton's third law, action equals to an opposite reaction, right? So for example, if you are pressing the table, you will also feel a force on your hands. That's the reaction of the table against your hands. All right? So if you push on the wall pushes on you. All right? That's if they come in pairs. If they are caused by forces, according to Newton's first law, you can be in equilibrium, or if there is a net force, then you can have a non-zero here. And then you have an acceleration. If they equal to 0, you will have no acceleration. So there can be either no change in velocity, or just the body is just standing still, so not moving. Okay? Acceleration implies a change in velocity. And Newton's second law, as you have it there, force equals to ma. All right? So this is a nice diagram there, all right, to summarize what we've been doing. So we sort of did that. Okay, so at this moment, you are exerting a force that should be downward, all right? That should be downward. At this moment, you're exerting a force downward on Earth. Is that true or false? Anybody? At this moment, yes, you are exerting a force downward, all right? And then by action reaction, the Earth is exerting a force towards you, the ground, okay? In the process of throwing a ball forward, the ball exerts a rearward force on your hand, a forward force on your hand, a rearward force on the ball. The hand exerts a rearward force on the ball. The only force present is your force on the ball. So what would you guys say? 1, 2, 3, or 4? What was that?
1.
1, exactly. As you throw the ball exerts a force on you in the opposite direction. All right? The way you can also see this is like, nobody has seen that here probably, but when back in the 1700s, when they were using those cannonballs, they will shoot, right? The ball with a very high speed. By action reaction, the cannon will recoil. Or the best example is if you ever go to a shooting range, right? If you shoot, you recoil, your hand recoils. That's action reaction there. Later on, we're going to talk about conservation laws, and there's something called conservation of momentum, but it also gets applied in here, in the action reaction of forces. All right? At one moment in a football game, player A exerts a force of 200 newtons to the east on player B. The size of the force that B exerts on A is what? And the direction is to the
West.
west. And what's the value of the force? 200, right? So, actually, can I use this? Oh, let me see. So, okay. So there was a way to write in there. Anyway, that's fine. So 200 newtons to the west. True or false? When you jump upward, the floor exerts a force on you that makes you accelerate. When you jump upward, the floor, the ground, the earth, exerts a force that makes you accelerate. That is true. All right? When objects fall, because when you jump, maybe you don't feel it, but then you will be accelerating towards the ground. And what did we learn last class? Accelerate with the value of gravity. Regardless of your mass, anybody, any piece of matter on Earth, when they fall, they accelerate with the acceleration of gravity. What changes is how they accelerate. Because, for example, we cannot say that a feather and a piece of iron, a hammer, will fall onto the floor at the same rate, at the same time. It doesn't happen, unfortunately, because of air friction. All right? But we know in the moon that actually is true. All right? Okay. So we've talked about these examples. I will then take a look at the worksheet I gave you guys in there. But before, let's finish with this, the law of universal gravitation. So this one is actually very interesting because the law of universal gravitation is not, it is and it is not. It is Newton's fourth law, but in many textbooks they don't even mention it. They say as first law, second law, and third law. And that's because Newton's fourth law, came or was published not together with the other three laws, and he was, I don't want to say hiding it, but it wasn't such a big deal for him apparently, because he was looking for a theory of gravity, right? And he developed one, and then it implied, or in some way it was used to prove the law of universal gravitation, right? So he didn't make such a big deal as he should have about it. So this is a major contribution because it allows us to explain the orbits of the planets around the sun, for example. You should remember that the Greeks, and then even Tycho Brahe and other astronomers, right? Not Copernicus, but other astronomers, they didn't accept that there were evidences that the Earth was actually rotating around the sun, right? The idea was that the sun was orbiting around the Earth, and the Earth was the center of everything. Then came the idea of epicycles. I don't know if you have heard about it, but that was the idea of the Earth rotating around an empty point in space. That doesn't make any sense now. We know that if there's an object rotating around another object, right? Like for example, the moon needs to rotate around the sun. The moon cannot just rotate around anything. There has to be a mass. And that's what Newton explained, that objects that are less massive than the sun are orbiting around the sun. Okay? That is the law of universal gravitation. You have two objects that are either attracting or repelling. If they are attracting, all right? So you have that objects seemingly seem to be falling towards another object, right? So the force that the Earth exerts on objects near its surface is just an example of universal gravitation, guys. The fact that we have satellites orbiting the Earth, it allows us to explain or to visualize gravity as it works, right? So the law of universal gravitation, in just simple words, is the idea that there is an instantaneous force acting on a body which is orbiting around another body that it's normally, is always more massive than the other body. So that's very, very important, because thanks to that, we're able to explain the orbit of the moon around the Earth. We're able to launch satellites and launch rockets to other planets, because we understand how gravity works. We probably don't know where it comes from, so that's different, right? But we know at least how gravity works. All right? So to understand this, we need to have an understanding of physics and mathematics. The orbit of the moon around the Earth is circular, almost circular. In fact, the planets around the sun, they actually have elliptical orbits that are very circularish. So we can use concepts on mechanics to explain that. So let me actually show you that on the board. Okay. Let's see. So now we know that objects like the sun, the Earth, and other planets, or the moon, they have the gravitational pull, right? So let's say we have the Earth. and we have an artificial satellite going around. How can we study the orbit of this satellite around the Earth? So, or how can we study the velocity, right, as it goes around? What makes the object go around? The gravitational pull of the Earth. So, from the center of the Earth towards the place where there is a satellite, we trace or we check the distance. The radius of the Earth is approximately 6,400 kilometers. And the mass of the Earth is approximately 6 times 10 to the 24 kilograms. So we can claim, and I'm actually exaggerating that orbit by the way, we can claim that a satellite here, as you go, right, is at an altitude of, let's say, 10 kilometers above the surface of the Earth. So this is the surface. So there's 10 kilometers from the Earth's surface to the satellite, right? So the whole distance will be 6,410 kilometers. All right. In a circular motion, the only force that acts on this body, and we're going to assume that is, and it's correct to assume that, is going at a velocity that is constant. Constant. We call that the orbital velocity. We have the orbital velocity of that. So now let me show you guys Newton's fourth law. So by studying the orbit of the planets, the orbits of even the moons, by checking their period, and by knowing Kepler's law. So by the way, the precursor of this, the person who came after, a precursor, was Johannes Kepler. You can Google it. He developed 3 laws as well. One of the laws was that the orbit of the planets around the sun is elliptical. And then he has the law of areas and the law of periods. Period squared over the distance cubed to the sun is constant. And don't worry about that. But the law of gravity, the gravitational law, states that the force of gravity, the gravitational pull, is proportional to the multiplication of masses divided by the distance squared from the center of masses. And you know what's the constant there? So it was discovered later that the constant, gravitational constant, is equal to 6.67 times 10 to the negative 11 newtons meter squared over kilogram squared. This is called the gravitational constant. So that's awesome, because now I know what's the force that anybody that is approaching the Earth is experimenting due to a gravitational pull. All right, which is that. And what's the force equals to? When the body is going in a circular motion, what force do I have in a circular motion? Does anybody remember? What's the name of the force in circular motion?
Centripetal force.
Perfect, yes. We have the FC, centripetal. And that's mass velocity squared over the radius, which is what? This. All this is R. So pretty much what you do is you make this force equal to that force. That's why you get orbital speeds. All right. Let's leave it there because you guys can see it. But that is the physics behind satellites. And that's how we can actually launch satellites. We cannot do escape velocity yet. You probably have heard about it. When you guys saw the mission just a few months ago, in the one from SpaceX, right? The one from SpaceX that happened in April, I believe. Yeah, April. They launched this rocket from Cabo Cañaveral to the ISS, and now just recently came back. When they launch it, they have to break through a barrier. They have to break through the gravitational pull of the Earth, which doesn't seem a lot, but it is. It can be a lot. All right? So we will study that more with energy. For now, this is very important. All right? Just to understand at least the ideas behind gravitational law. How do we use it? All right? Something that is also used for is the idea that gravity is also affected by this, right? So we know that when we talk about the force, the gravitational force depends on, we know already that Fg is a force, which is the force of gravity. And the force of gravity depends on what? The mass and gravity. Mass doesn't change, but gravity does. That's important. We know gravity is not constant, right? The value of gravity depends on where we are located on Earth. Inside the Earth, or on Earth, right? When we are on Earth, it doesn't really change by much, maybe 9.80, 9.81 meters per second squared, right? So by 100th, right? But as you go farther from the center of the Earth, that value of gravity starts decreasing. All right? So how? Let's put the equation here. I'm gonna write the equations for, or the equation for Newton's fourth law. So the gravitational law is written as G m1 m2 over r squared, where r is the distance. The masses are m1 m2, and you know g is just a constant. So let's suppose you are here on Earth. Two situations. One situation where this is the Earth, and you are standing here. And the other situation where you are here, but then look, you are farther from the center. Here you are closer. At this point, your weight could be 700 newtons. In this case, your weight could be 400 newtons. Where did the other 300 go? This will be M2. So mass times gravity is the weight, the gravitational force. So let me introduce you guys to the equation of gravity. This is M1, this is M1. What you're seeing there right now is the equation of gravity. So it makes sense. The farther you go, the smaller gravity will be. Alright? That's why when you are farther, as you get out farther from the earth, gravity starts diminishing until you start floating, right? Let me show you this slide. There. That's Newton's law. You know what's interesting? That's called the law of universal gravitation. Nowadays we know that that's not very accurate. The law of universal gravitation works for objects that are not very massive and that are not behaving at very high speeds. When you go into higher astrophysics or particle physics, when you go into very high speeds or very high masses and speeds as well, by the way, like for example, electrons in the accretion disk of a black hole, or let's just say stars orbiting a black hole, like in the galactic center, this idea doesn't really work anymore, right? In fact, let's just go local. When you want to explain orbits of the planets, everyone works except the one on Mercury. It works and it doesn't work. It works at some points, it doesn't work to explain certain anomalies. One of the anomalies of Mercury is that Mercury is preceding the perihelion. Okay, so just a few concepts, right? When a planet orbits around the sun, there is the aphelion and perihelion. The perihelion is the shortest distance between the planet and the star. So the perihelion of Mercury is preceding. It's not always in the same position. You cannot explain that with the law of gravitation, even though it's a law. It doesn't work in that particular situation. So what do we need? We needed Einstein. 200 years after Newton, 200 each, right? He developed the special, and then the general relativity, where he joined the concepts of light, the speed of light, and the effects of gravity. And then, even though I said that we know how gravity works, but we don't know where it comes from, at least now we are certain gravity warps space-time. So it's correct to say that gravity works as a force, but it's not totally correct. Gravity, for example, the Earth that you see there, imagine the space where we are is like a fluid. The Earth is pushing against that fluid, the gravitational pull. And even though we don't see it, we can measure the effects. And we have seen that by looking at light. Light gets deflected by gravity. So if gravity is affecting light by bending light, there has to be a higher concept of gravity that Newton didn't have access to because of the tools, because of the math, right? Because of time as well. I mean, he developed a lot of things, but that was not the case, right? So that's very interesting, right? Now, applications for this will just be, they give you two masses and they ask you to find the force between two masses, right? So they give you two people of 70 kilograms and then you can measure it, right? Depending on the distance, of course, but again, the mass is very low to make any difference. All right, we see the effects of this more when we're talking about the gravitational pull. And by the way, in the slides as well, so you can also see there, that's the equation for gravity. And the mass of Earth, approximately 6 times 10 to the 24. What can I ask here? A conceptual question will be, what are the parameters that affect gravity? The mass and the distance from the center of the planet. The closest you are to the center, the higher gravity is. All right? So that's why we know that gravity inside a black hole is enormous. Because a black hole is millions, in some cases billions, the mass of the Earth. And the radius is very small, right? It can be a few thousand kilometers, no more than that. There can be black holes the size of the Earth, but with the mass of the whole sun, or even twice the sun contained in there, right? So that's what we know as a singularity, okay? That's very nice. Here in this table, they give you values of the acceleration of due to gravity on different places. So for example, we can see, as I said, gravity depends on the mass and the rate. For example, right? When you want to know the mass or the gravity on certain planets or the stars, you need to know the mass of the star or the planet and the radius of the planet or the star. And then by knowing those values, you use a formula gm over r squared, and then we can get, in fact, I'm going to do the calculation so you can see it for the Earth. All right? Then we have the sun, the moon, very small. Man, you know what the problem there? Look at the gravity of Mars. When people ask me if we are going to be able to colonize Mars one day, I wish Mars was more like Venus, even though we know Venus is hell on Earth, right? Venus, it's a nightmare for people who fight, for people like that are against this whole climate change that is going on. We don't feel it right now, but the effects are going to be felt probably in the next 50 to 100 years. Not like Venus, but there are going to be some changes, of course. Venus has a very strong greenhouse effect due to the very dense and poisonous, by the way, atmosphere. So nothing can live on Venus. Well, maybe you read the news and you probably heard that we're trying to see if there are some signs of even organic life, but that's not on the surface of Venus though. They're trying to look on the top of the clouds of Venus. So when you go within the clouds, there is a lot of ammonia, there's a lot of carbon dioxide, a lot of sulfuric acid rain that will kill anything organic. But on top of the clouds, we think that there are evidences for it. But anyway, that's another thing. What I mean is that the gravity of Mars is very weak. So I don't know if Mars will be an appropriate place to colonize. I always feel like it's more like a science fiction, like Total Recall and stuff like that, but it's not really very suitable. Jupiter and Saturn, forget it, because they are gas giants. There's no surface. So the other planets, the only places where we can think about colonizing one day is Mars and maybe the moons of Jupiter or Saturn. The problem is that they are very far from the sun, right? Venus and the Earth and Mars, they happen to be in the Goldilocks zone. The Goldilocks is a definition of not too hot, not too cold, right? So it's a nice distance, but still, I still find it very hard to think or believe that we can have bases on Mars, but living on Mars is a different story though. So let's do a calculation. And we're about to finish with chapter 2, by the way. It's not bad. So remember, quiz on chapter 2 on Tuesday, okay? And then we go into chapter 3. Don't forget to do the assignment. And actually, before we finish, I want to show you a few of those problems with that there are in the extra credit sheet. Okay. Knowing that we're going to use approximations anyway, but let's see what we get. The mass of the Earth is 6 times 10 to the 24. It's actually 5.978, but times 10 to the 24, but it's good anyway. And knowing that the radius of the Earth. But remember, this is in kilometers. So I have to do, right? I multiply by 1,000. Let's use the equation. Let's try to find gravity. Gravity is the gravitational constant, the mass of the Earth, divided by the radius of the Earth square. G M over radius square. Let's do this. 6.67 times 6 divided by 64 squared times 10 to the negative 11 times 10 to the 24. That gives you 10 to the 13. You add the exponents, right? But one is negative. And then you have 10 to the 13 divided by 10 to the 5 squared, 10 to the 10. So now I will do the calculator here. 6.77 times 6 divided by 64 squared. I get 0.00977. So I get this. 0.00977 times 10 to the 3. If I move the zeros, 1, 2, 3, I get, for my gravity, I get this. 9.77 meters per second squared, which I can approximate as 9.8 meters per second squared. There you are. This was very important. You can see that equations that were discovered more than 200 years ago, they give us values that we can actually work, right? So that's basically it, guys. I want to show you for chapter 2. What I want to do now, we have a few minutes, we have some time left. I want to show you just a few hints for the problems in the worksheet, all right? If you try to solve them, there is a couple in particular that I want to make sure that you guys have it clear. And then with that, I think we can call it off for today, all right? If you have any questions, please let me know. Maybe on Monday, I could try and do office hours, all right? I will publish it and then you guys can let me know what time works best for you if you have any questions, but I think there shouldn't be much of an issue. The quiz is not difficult. For the test, I might give you a guide. I still haven't decided when we're going to have the first test. It might be once we finish chapter 3. We have our first test. All right? So, motion, Newton's laws, and energy conservation and momentum. That will be the first test. I think that will be good to have a first test. All right? Anyway, so let's take a look at some examples. All right? And let's just show you what I have here. I think we can close this now, and then close this, and then here in the home page, there is this here. Let's give you a few ideas of how to do this. If a net force accelerates a mass at 40 meters per second squared, what should be the force for an 80? Okay, so the same force, right? find the force, and then use that force to find the acceleration of this mass. Nothing difficult there. All right. We did this problem last class. A car with certain mass traveling with initial speed. You have that it comes to a complete stop, so the final speed is 0 after some distance given there. So actually, here, for that example, if they give you a mass of, for example, 1100 kilograms, and it's traveling at some initial speed, I suppose is this, after traveling this distance, it could be 600 meters. I'm just making out the numbers right now. It will stop here, right? So the final velocity, how do you get the acceleration for that particular problem? Remember this equation. V final squared equals to V initial minus, plus or minus 2a delta x. But because it's slowing down, it will be V initial squared minus 2a delta x. And what's V final? 0. 0. Initial delta x, delta x. So you find the acceleration, and then you do force equals to mass plus acceleration. All right, that's for that problem. Problem 4 is a very interesting one, and I like to at least you guys do the forces diagram. If there was a problem like that on a test, right? I could give an extra point if you solve the problem, but let's see how you do it. They give you two masses. I want to change the masses to make it more doable, like more simple with the mathematics. It's the same idea though. You have a table like this, and then on here you have a pulley. You know, a pulley is a device that you use if you guys go to the gym. Every machine has pulleys. That's where the weights are. So using the concept of forces, that's another application, by the way, of this topic. You can actually have a machine where you carry weight, right? So a pulley is a nice device for this type of topics as well. So you have a mass, and we're going to assume no friction, right? No friction in any surface. Let's say this is 15K. And there is a whole rope, and you have here another mass. For this mass, we're going to assume 5K. Obviously, the system will move like that. No friction, right? Nothing to stop it. So, how do we find the acceleration? This, as soon as they tell you acceleration and motion, you have to remember this. Second law. So if you attempt this problem, remember, Newton's second law. The net force acting on the body is equal to mass times acceleration. So we need to see what forces are acting on the body that are making those objects move. For 5 kilograms, right? Let's not forget this. For 5 kilograms, there is what? The weight, but there is a rope. Whenever they give you a rope, guys, there is tension. All right? So here there is a tension there. we call it T. Because the pulley, there is also no friction in the pulley. They say no friction anywhere. So we can assume that there is also a tension there. And here, there is also the normal, right? There. Now, we can find the value of the weights, mg. So if you go to the calculator, and we do 5 times 9.8, 49. This is 49 newtons. And 15 times 9.8, 147. So this one will be 147 newtons. The weight of 15 doesn't matter because 15 is on the ground. What's making 15 kilograms move is the tension to the right. What's making the 5 kilogram move? The force of gravity. So, Newton's second law here. That's what normally students get confused. What is the net force? You need to remember vectors, directions, magnitudes. There is a force pushing it downwards, 49. But there is also a force pushing it upwards, the tension. So the net force for this will be 49 minus tension equals to 5 acceleration, ma. And then for the first mass, the tension is equal to mass times acceleration. That's why this is more like an extra credit problem, like a challenge. Not because of the physics, but because the math can actually, but as you can see, it's just a simple substitution, right? If you substitute T here, you will get 49 equals to 28, right? You substitute this here, and by solving the equation, you get that. The acceleration should be around 2.49 meters per second squared. So around 2.5 meters per second. What can I ask on a quiz? Just the forces diagram. That would be a good idea. Or even on a test. Just do the forces diagram on that body. All right. So that will help you for that. And I think there's only 6 problems. Oh, a lot. So the first 4 or 5 are very similar. So I think you guys can do that with no issue. All right. If you are interested on going into the applications, right? The quiz on Tuesday will be very similar to the quiz that we have last time, so I'm sure you guys will be fine. I'm gonna try to make sure that you guys don't have any issues submitting it. All right, so this time you can submit it through Canvas, and you can get your grade, and you can see the corrections there as soon as I grade it. Okay, make sure you work on the homework, and that's it, right? The lecture has been recorded.